You're listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Hey folks, welcome back to the MedX Podcast. Today's guest is Scott Nelson, CEO of FastWave Medical. FastWave Medical is developing the next generation of intravascular lithotripsy technology to advance the treatment of vascular calcification. Enjoy. Hey, Scott, thanks for joining the MedX Podcast today.
Thanks for having me on, Steve. Yeah. Really looking forward to the chat.
I'm really looking forward to understanding the advanced technology in intravascular lithotripsy, IVL, for the treatment of calcified arteries. And I know this technology, lithotripsy, has kind of been around for decades, right, to treat kidney stones. But more recently, maybe in the last 8 years, this disruptive technology of IVL has come on the scene. And I think within the last year, it's really been under the spotlight because of a huge acquisition in the space by one of the strategic OEMs acquiring one of the incumbents. So really glad to have you on to talk about this technology. And if you can kind of just paint a picture of the clinical need for IVL and then go over the FastWave platform.
Yeah, absolutely. And you're not the only one that struggles pronouncing lithotripsy, right? It's easier just to say just to say IVL. And right. In fact, that's the acronym that's probably most often utilized kind of in the public domain anyway. But Steve, you're exactly right. Lithotripsy, probably a lot of the folks listening to this have heard about it within some context. And it's been around for probably 3 decades plus now, at least, largely utilized for the treatment of kidney stones. So extracorporeal lithotripsy is kind of where maybe people that have heard about it before are used to the term. So with that said, intravascular lithotripsy, or IVL, is kind of a newer technology, relatively speaking. FastWave Medical, which is the company that was recently acquired by J&J that you referenced, is the kind of that created this category, and largely leveraging kind of the mechanism of action with extracorporeal lithotripsy and applying it within a balloon technology. And so FastWave, I'd have to go back and look at. They've been around for the better part of 10 plus years, and have done an exceptional job. It's really a kind of a unique story in the world of med tech. You don't see $billion-dollar. You don't see startups too often IPO and then eventually become acquired for $1 billion. So credit to their team and for building a market. But with all of that said, as a kind of a first generation type of technology, as most people would expect, there's some gaps to fill, right? And that's what we're trying to do with FastWave. But to kind of circle back around to your question, like what is this, right? IVL is utilized within the cardiovascular space today for peripheral and coronary applications to crack or create fissures in plaque in order to increase the luminal space within a blood vessel, right? So most people are familiar with kind of plumbing. Best to kind of use that analogy. You've got a clogged pipe. If that clogged pipe is burdened with excess calcium, that historically is hard to treat with traditional POBA or specialty balloons or atherectomy, and that's where IVL really shines. Is to treat that calcium buildup in a blood vessel, with the end goal of again creating more space in the vessel to eventually lay a stent in most cases, especially for coronary applications. So hopefully that high level kind of overview helps.
Yeah, absolutely. Some of the predicate or traditional technologies, like you mentioned, plain balloons, maybe atherectomy, cutting balloons. Would IVL still work in a synergistic way with these existing platforms?
It does, and maybe I'll it's kind of utilized differently for peripheral and coronary applications. But considering 80% of the market utilization of IVL is generally for coronary applications, we'll kind of stick to that. That application anyway. But there's kind of a default algorithm, right? And this is that most high risk PCI operators utilize, where They'll first start with imaging, right, to get a sort of a lay of the land, whether it's IVUS or OCT. Once it's determined that there is, in fact, calcific burden, kind of depends on the nature of that calcium, whether it's medial placed, if it's eccentric, if it's more circumferential in nature, depending on kind of that answer. If it's more concentric, as an example, most interventional cardiologists will start out with IVL, in fact, first, as kind of their default tool of choice, largely because it's so safe and so simple to use, right? Versus, the alternative when it comes to plaque modification, trying to modify plaque and get it to become a little bit more compliable, if you will, is atherectomy. And atherectomy, especially for coronary applications, is, comes with more technical risk, more risk overall, especially more technical risk. It's, I would argue maybe it's not as safe, definitely not as easy to use versus IVL. So a lot of physicians these days will start with IVL. And then after IVL, kind of go back in with another imaging catheter to get a sense for how well it worked, how much luminal gain they were able to achieve, and then based on that answer, they'll utilize other therapies, right? In some instances, they may go back in with a non-compliant balloon before laying a drug-eluting stent or a DCB. If it's more challenging plaque and they maybe IVL didn't work as well as they thought, maybe they'll go back in with atherectomy, to try to again create a little bit more luminal gain, because at the end result, the end case being, in most situations, you're going to lay a stent. You want that vessel to be prepped as best as possible before laying that stent, and that's where that's where IVL has really become quite popular as a plaque modification kind of vessel prep tool.
Okay. The key word I got out of that was, simple, right? It's not a complicated procedure. So that'll always help you going forward. Yeah.
In fact, I like to think of in terms of why IVL has taken off like it has, right? I like to think of it as like a four-legged stool. One is it's very simple to use. Most fellows that graduate from any sort of fellowship, even the lesser known fellowships, right? They understand how to use an angioplasty balloon, right? And this is just energy powered, angioplasty. Secondarily, it's safe. The safety profile is very, 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 very good. Third, it works, right? It works quite well, especially for a challenging disease in calcium. And then fourth, the reimbursement, at least here in the U.S., is very good for it. So it's kind of those four reasons all add up to why it's taken off like it has.
Excellent. I know that you're still in kind of the early stages, or I know there's clinicals and a lot of work going on. It might be difficult, but would you be able to kind of give us a comparison of the incumbent technology to FastWave as far as crossability, deliverability, energy delivery, and pulses, and some of those key factors?
Yeah, absolutely. And I'm certainly not going to knock Shockwave, right? Yeah. And that's not the intent in my answer, because they've done a phenomenal job in creating a category, and kudos to any company that creates a category, right? It ends up kind of succeeding the way they have. So again, credit to their team. But as I mentioned, with any first generation technology, there's just inherent gaps. And we, as kind of a sort of a fast follower into the space, we have the sort of the advantage of quickly identifying those gaps and trying to be able to solve for them without sort of the burden of doing this with a commercial product, as an example, right? So some of those key gaps are, I'll mention just a few, right? So crossability and deliverability, right? Yeah. As you can imagine, you're designing a balloon technology that produces shockwave. So there's some sort of energy component that you're having to build inside of the energy producing component that you're having to build inside of the catheter, which impacts crossability and deliverability of the balloon. And that's probably one of the biggest challenges that most physicians bring up when talking about shockwave, and what they wish it would do better is they wish they could get it to more places, right? And some of that's just because of the inherent nature of vessels that are burdened with calcium, right? They're going to be more tortuous. They're going to be harder to navigate. But with a bigger kind of bulkier balloon, that's especially problematic. So that's one key area that we're trying to really address, is crossability, deliverability, trackability of the balloon technology. Secondarily, there's pulse limitations, right? So shockwave catheters offer a certain number of pulses depending on the application, right? Coronary is going to be different than peripheral, as an example. But with multiple vessels that are diseased with calcium, you oftentimes run out of pulses, right? Physicians will simply run out of them. And so they'll have to kind of parse the number of energy pulses based on the case. And so that's another key area that we're trying to improve upon, is just, being able to offer more energy, so to speak, in general. And then third, and this is getting into the weeds a little bit, but kind of based on the shockwave design, there's limitations around treating eccentric calcium, right? So think about the cross section of a vessel. If the calcium is sort of positioned from 12 o'clock to 3 o'clock, right? If you're thinking about a clock in the cross section of a vessel, current shockwaves technology doesn't do the best job when it comes to eccentric or nodular calcium, and so with our technology we're trying to improve upon sort of the better overall kind of sonic pressure in terms of it's circumferential in nature and providing more sonic coverage in general. So those are a few key areas amongst others that we're trying to improve upon.
I read about the use of potentially longer balloons, and I wasn't sure why. Is it for more emitters, for more pulses? Is that the general theme there? Can you talk a little bit?
Yeah, and kind of sticking to coronary. I mean, this is certainly applicable to peripheral applications as well. But even with coronary balloons, Shockwave's longest length is 12 millimeters, which is okay, but pretty short, for the most part. And when you're treating vessels again that are burdened with more calcium over kind of longer segments, if you will, in essence, a physician has to kind of take that balloon up and down through the course of that vessel. And so, longer lengths are certainly another area that we're trying to improve upon. And some of that, what drives the sort of the constraints around longer lengths is those emitters, right, that you mentioned. You in essence have to build more emitters inside the balloon in order to develop a longer balloon, and that adds to the crossability and deliverability of the balloon. So there's always sort of that trade-off with emitter-based technology, and so we're definitely that's definitely an area that we're trying to solve for as well.
Okay, yeah, it's a double-sided coin there. You're fighting against each emitter. Yeah,
exactly. Yeah,
okay.
That's probably one of the unique things about FastWave is that because we're developing two different energy platforms in parallel. One is, I would kind of frame it up as what we consider kind of a me better version of Shockwave. It's kind of emitter based sort of technology. The other platform is not, right. It's not an emitter based platform at all. Largely rooted in trying to solve for some of these key constraints that we've discussed. By moving away from kind of an emitter based technology in general allows you to overcome some of those inherent hurdles.
Gotcha. Maybe increased deliverability, crossability without the emitters.
Yeah, you got it.
Profile. Gotcha. Okay,
you
makes sense. Excellent. Thanks for going through that. I think our listeners will be very interested in that. Now that we kind of have a kind of an overview of the technology and we're in FastWave's technology, can you kind of give us an update on where the company is to date and what are some of the milestones and where do you see yourself, the next couple of years?
Yeah. So we're FastWave is a relatively young company. We incorporated in 2021, raised our Series A later that year, in July of 2021, and have since raised a couple more rounds of capital. We completed our first in human feasibility study with one of our IVL platforms, and sort of the next major inflection point with that particular platform is to get into a pivotal trial. Which we're aiming for soon, probably early next year ish, kind of time frame. And then the other platform that's what we think of as kind of a true next generation type of IVL technology, that sort of emitterless platform, if you will. We're quickly approaching first in human feasibility work with that technology, with the goal of getting into IDE studies next year in 2025.
Excellent. Very exciting times.
Yeah. A lot of we're through, I would say, a significant amount of technical kind of development work. Not all the way through, as you can imagine, with an early stage company, but we feel really good about kind of where we're at from a development standpoint. But the next major milestones are kind of correspond to a lot of clinical work. So pretty exciting.
Excellent. Hey, Scott, this has been a really great conversation. I know it's been short, but it's to the point, and you gave us a good understanding of IVL, the technology, and where you're at with it, and wish you guys the best of luck.
No, thanks for having me on. Yeah, it's always fun to talk about IVL. So yeah, really appreciate the discussion.
All right, thanks, Scott.
Thank you for listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.